So to try and understand this, we're going to work through this example. I'm going to do out the table on this page and then graph it on the next. So plot the graph of y equals 1/2 to the power of x in the domain -3 to 3. So I have written out -3, -2, -1, 0, 1, 2, 3 into my table. So I'm going to start working this out now. So let x equal -3. So I'd have 1/2 to the power of -3. That minus means that I can get the reciprocal. So that gives me 8. If I let x equal -2, that minus in my index, in my exponent, means I can flip it. And I get 2 to the power of 2, which is 4. And so on. So I get 2, 1, 1/2, 1/4, and 1/8. Okay, so I'm going to attempt to plot this on now. So if I start at -3, 8, and then I've got -2, 4, then I have -1, 2. Like with the graphs previously, it's going to cross over at 0, 1. 1, 1/2, so at 1 it crosses over at the base. 2 is 1/4, and then 3 is 1/8. Okay, so now I need to start connecting these up so I can have a look at the shape. So this is going to be a curve, so we're not going to have straight lines. So if, like me, you find it difficult to just do kind of one line, it sometimes is useful to do kind of little dashes as you go along, just to make sure you're getting the proper shape. And that's what it looks like. So this would be a decay model. So it starts off with a certain value, and you can see that it drops. So it's actually almost like the opposite relation to the growth one. This is the decay model. Okay, so I'm going to show you an example of where I've seen this in real life. Okay, so here's our two different style of exponential function. So the growth one, so the growth model is where you have a to the power of x, and a is any number greater than 1. And then you have the decay model where you have any number between 0 and 1. It starts off quite high and then drops, and you'll see that it approaches 0 but will never actually reach 0. Okay, so that is our decay model. Okay, so we're going to have a look at the transformations of these graphs. When we've studied transformations of graphs before, we've had a look at magnitude. So that was where you multiplied the function and then it changed the shape. So if we were looking at, say, a quadratic function and you changed the magnitude, it became something like that. Okay, then so we had a look at that. We also had a look at reflection. So that might have been where you have multiplied by -1. And we had a look at translation. Okay, what we're going to have a look at for this section is the magnitude, and we're going to have a look at translation as well. We're not going to need to look at reflection. Okay, so copy and complete the table below. So we have a function that's 2 to the power of x, and we have another function that is 4 times 2 to the power of x. So I've explained this before, that is the dot product. Sometimes we use the dot not to represent the decimal point, but to represent multiplication. But if it makes more sense to you, you can write that as 4 times 2 to the power of x. Okay, so we have our basic function 2 to the power of x. So 2 to the power of -1 is 1/2, 2 to the power of 0 is 1, 2 to the power of 1 is 2, and 2 to the power of 2 is 4. So then 4 times 2 to the power of x is simply going to be each of those values multiplied by 4. So we have 1/4 times 4 is 1, 1/2 times 4 is 2, 1 times 4 is 4, 2 times 4 is 8, and 4 times 4 is 16. Okay, so we're going to plot that onto a function on the next page, and then we're going to use our function to estimate f of 0.5. And hey presto, here's one I made earlier. So f of x is the blue one there, and we were asked to find, using the graph, an estimate for f of 0.5. So if I go to the graph and find 0.5 on my x-axis, I'm going to draw a dotted line, preferably using a ruler, up until I meet the graph, and then I'm going to move across. Okay, so I can see that that is about 5.5. So my estimate is 5.5. Okay, there's actually something really noteworthy about this, so I'm going to just make a note of it here. As you can see, our original graph in the form of a to the power of x, which was 2 to the power of x, had a y-intercept of 0, 1. This has changed. So when you have something where it's like b times a to the power of x, so you have some kind of coefficient, your new y-intercept is going to be that coefficient. Okay, so if ever you're looking at an exponential graph and you see that it doesn't cross over at 0, 1, the first thing you might check is, has it been multiplied? Has the magnitude been changed? So if we take a note of that now, if a function is of the form f of x equals b times a to the power of x, then the y-intercept is 0, b. So in our example, the coefficient was 4 and it crossed the y-axis at 4. So for any value, it's going to cross the y-axis at that value. Okay, so here's an example of how that could be asked. The given curve represents either f of x equals k times 2 to the power of x, or b, which is f of x equals k times 3 to the power of x. First part asks us, find the value of k. I can see that the y-intercept is at 0, 5, so I know that k equals 5. Okay, so my coefficient gives me the y-intercept, and my y-intercept gives me the coefficient. So part 2 is write down the function that the curve represents. Okay, so what we need to do now is sub these values into a and b and see which one it works for. So f of x equals k times 2 to the power of x, which we know to be 5 times 2 to the power of x. So if I sub in 2, I should get 20 as my answer. So f of 2 equals 5 times 2 to the power of 2, 5 times 4, which is 20. So it does work for that function. So I can probably guess it's not going to work for the other function, but I'm going to go through the motions with you anyway, just to kind of prove the point. So on B, we have f of x is k times 3 to the power of x. So we know that that k is 5. If I sub in 2, I should get 20 for my answer. So f of 2 is 5 times 3 to the power of 2, which is 5 times 9, which is 45. So that very clearly does not work. So write down the function that the curve represents. It's f of x equals 5 times 2 to the power of x. Okay, so now we're going to have a look at translation. So this one I suppose would be more rare in comparison to the previous one. I haven't seen it as much in exam questions, but it is relevant and quite useful, so we're going to go through it anyway. Draw a sketch of the function f of x equals 3 times 2 to the power of x plus 2 in the domain minus 2 is less than or equal to x, which is less than or equal to 3. So we're taking values from -2 to 3. Once we have that done, we're going to write down the range of the function. So in order to do this in a kind of quick and easy kind of way, I'm going to show you using Desmos. Okay, so we're going to have a look at this through Desmos. And if you think about it, the basic function was 2 to the power of x. That was our basic exponential function. And you can see that on the graph there in blue. And then the function is multiplied by 3. So you should see that the magnitude has changed. So everything is just going to move that bit quicker. Every value has been multiplied by 3. So it just moved up. It's changing a bit quicker. And then the last thing is that the function, is going to be translated. So we're going to take our function 2 to the power of x, multiply by 3, and then add on 2. Okay, so that has again moved the y-intercept. By multiplying it by 3, the intercept of 1 was multiplied by 3 to give us 3, and then the 2 has moved it up the graph. So it's taken the graph and has moved it up 2 places on the vertical so that it now crosses at 5. Okay, so here's a question that's going to test out some of the things we've learned so far, but should also help us learn a little bit too. So the graph of the function is given to us on the right. It's y equals ae to the power of x plus b. A and b are unknown. E is a value that we learned about earlier. It's an irrational number, and E was approximately 2.718 and so on. You can correct me if I'm wrong. So what we have to do is try and find out what A and B are. Remember that A changes the shape, it changes the magnitude. It's going to rise a lot quicker depending on what A is, if A is bigger than 1. And then here, B is how it's been translated, so how it's been moved up or down. But both of those can have an effect on the y-intercept. So if we have a look at the graph, we have been given a coordinate, 1, 14. So that means that when x is 1, y is 14. But we've also been given another point here. We've been given that point 0, 0. So when x is 0, y is 0. So what I'm going to do is I'm going to use those pieces of information and I'm going to sub it in to the function and find out what the values of A and B are. So y equals ae to the power of x plus b. So if I sub in 0 for y and 0 for x, that leaves me with 0 equals a. E to the power of 0 is 1 plus b. So we have a plus b equals 0. Using the other coordinate, I've got 1, 14. So that leaves me with 0. Apologies, I'm getting carried away again. That leaves me with, instead of y, I have 14. I have a, instead of x, I have 1 plus b. Okay. So as you can see, it looks quite a lot like I've got simultaneous equations here. So I can go about this by using elimination, which we used most frequently at Junior Cert, or I could also use substitution. I'm going to use substitution. You can use either, but I just think substitution might be the easiest one here. So I'm going to let a equal minus b. So I've got minus b e plus b equals 14. If I factorize the b there, I have minus e plus 1 equals 14. So b equals 14 over 1 minus e. So that's going to be an irrational number. I'm not going to bother writing that out, and I was told to leave my answer in terms of e. The next one then, I need to find out what a is. A was minus b, so a is minus 14 over 1 minus e. If you want, you can write that as 14 and just apply that minus to the denominator and you get that. Okay, So there is the solution to that question.